Hi, welcome back to maths class. Today we're looking at finding the derivative of log functions. So if I look at the natural logarithmic function that I've got there, f of x equals log base e of ax plus b, I can see that the argument of the logarithm is a linear function ax plus b. Now remembering that that always has to be positive, it can't be 0 or negative. That means that if I've got ax plus b greater than 0, if I solve that for x, I'm going to get ax is greater than negative b, which gives me x is greater than negative b over a. So that's why I need to specify this for this function, okay? So that's my function. Then this is my derivative. F dash of x is going to equal the coefficient of x from in here over the linear function that's in here. Now log functions are kind of weird because the derivative feels like it's got nothing to do with the original function. It's the least intuitive of all the derivatives we're going to do. So this is one of those ones that you definitely need to just write in your books, write it somewhere prominent, and make sure you can always check it. The derivative of the log function is not intuitive. So we just need to write down the rule and make sure we've always got access to it. So now let's practice using it. My first example, I'm going to find the derivative of a straightforward example, log e of 2x plus 3. That's f of x, so f dash of x is going to be the coefficient of this linear function, that's 2, over the original function, 2x plus 3. Done. Not very intuitive, but not very hard. Okay, now we're going to do this next example, okay, and the key here is looking at it carefully and recognizing, ooh, that's not a linear function. So I can't just go straight to this rule here and put a over ax plus b. In fact, what I have here is a composite function. So I need to identify my inside and my outside function. If f of x is log base e of some other function, then this function inside the argument of the logarithm, that is my inside function. But also because I like to use the dy dx notation, I'm going to first redefine this and say let y equal log base e of x squared plus x. Now I'm going to define u as the inside function. And now I'm ready to rewrite y in terms of u. Y equals log base e of u. Okay. Now I need to find the derivative of y with respect to u and the derivative of u with respect to x. dy du equals, let's have a look, log base e of u. If I look at my rule, I'm going to have the coefficient of the linear function divided by the original function. All right, what's the coefficient of u? It's 1. What's the original function inside here? It's u. I'm done. Now I need to find du dx. Du dx is 2x plus 1. Okay, I didn't leave myself enough room here, but we'll squeeze it in. Now I need to apply my chain rule, and to do that I'm going to use dy du times du dx in order to get dy dx. So dy dx is going to be dy du is over here, 1 over u, but let's replace u with x squared plus x times du dx is 2x plus 1. I'll just rewrite that, 2x plus 1 over x squared plus x, and because I started with f of x notation, I'm going to write f dash of x here equals 2x plus 1 over x squared plus 1. Now what I want to point out to you is that what I've actually got here, this 2x plus 1 is the derivative of the inside function, and the denominator is the inside function. So what I have here is the derivative of u over u. And I'm going to show you this one, and we're going to see that we're going to actually have the same rule happening. So for my third example, f of x equals log base e of e to the power of x minus e to the power of negative x. So the first thing I want to do is redefine it. Let y equal log base e of e to the x minus e to the negative x. And then I'm going to let u equal e to the x minus e to the negative x. And now I have to differentiate this du dx. The derivative of e to the x is e to the x minus the derivative of e to the negative x. Now the derivative of e to the negative x will be, that's my coefficient, so it's going to be negative e to the negative x. Because it's already subtracted, it's going to be negative e to the negative x, so it's plus e to the negative x. I can't simplify that. I'm just going to leave it as it is. So now I rewrite y in terms of u. That's log base e of u. I've already done this one just up here. dy du equals 1 over u. So now to find dy dx, I multiply those together. dy du, that's 1 over u, times du dx, that's e to the x plus e to the negative x, which gives me e to the x plus e to the negative x over u is e to the x minus e to the negative x. So what I have again in my derivative is on the numerator, I have the derivative of the argument of the logarithm, and on the denominator, I have the argument of the logarithm. So that leads me to generalize that rule. What I can do here is say that for any function log base e of f of x, the derivative is going to be the derivative of this argument, the function that's in the argument, over the original function that's in the argument. No logarithm appears anywhere in the derivative. So let's do one more example using that rule. I'm going to find the gradient of the tangent to the curve of y equals log base e of 3x squared minus 2 at the point where x equals 1. So the first thing I need to do is find the derivative. dy dx is going to be the derivative of 3x squared minus 2, so that's 6x over 3x squared minus 2, the actual argument inside. As long as you've got your rule written down somewhere, these are not hard. Where people run into trouble is when they don't remember this rule or can't find it or don't use it. So you've got to find the right rule. 6x over 3x squared minus 2. But the question didn't ask me for the derivative. It asked me to find the gradient of the tangent to the curve. That means the value of the derivative when x equals 1. So now I just have to use x equals 1. dy dx is going to equal 6 over 3 minus 2, which equals 6. Oops. And that's the answer. And we're done.